Let's look at an example with some equipotentials with some nice numbers so that we can practice using equipotentials to make estimates and understand field behavior. Let's suppose that I have a charge. My charge is, let's say, 10/9 of a nanocoulomb. Why would I do that? You'll see in a second. I know that my Coulomb constant is 9 times 10 to the positive 9 Newton meters squared per Coulomb squared. So what that tells us is that our Coulomb potential for this point charge is going to be KEQ over R. So that is 10/9 times 10 to the minus 9 times 9 times 10 to the plus 9. So my factors of 10, powers of 10, are going to cancel each other, and 10/9 times 9 is just 10. So this potential will be 10 over R. Now, we'd like to have a graph with evenly spaced voltage values. So let's suppose I would like to know where is the voltage equal to 500 volts. And if you're curious, this is with reference to saying that 0 volts is at infinity. So 500 volts would occur where 10 over 500 is equal to R. So that is 0.02 meters, 2 centimeters. Where would we have 400 volts in this example? We'd have 400 volts at R equals 10 over 400, or 2.5 centimeters. 300 volts contour would be located at R equals 10 over 300. So that is 3.3 centimeters, or 0.033 meters. 200 volts. The 200 volt interval would occur at 10 over 200, or 5 centimeters, 0.05 meters, and 100 volts will be located at R equals 10 over 100, or 0.1 meters, 10 centimeters away. So let's take a look at a graph with these 5 contour intervals that show us evenly spaced values of voltage. I hope you can see that they're getting further apart as that surface becomes less and less steep, meaning the electric field is getting weaker as we go further away. So we're looking at this example where we had 10/9 of a nanocoulomb located at the origin and 5 equipotentials. These equipotentials are showing lines of constant voltage at different distances from the charge, and we had 500 volts at 2 centimeters, 300 volts at 3 1/3 centimeters, 100 volts at 10 centimeters, etc. And this is projecting a 2-dimensional representation of this 3-dimensional potential surface. But this contour plot gives us some power. Suppose we wanted to estimate something like electric field at some location. Well, I could estimate the electric field here, halfway between these two radii, let's say at in between 0.05 and 0.05 and 0.1 meters. I know the electric field is going to point away from this central charge because it's a positive charge, so it's pointing straight away. And how big is that electric field? Well, I know the size of the electric field is going to be the change in voltage over the change in distance. So in this case, that's going to be 200 volts minus 100 volts over 0.05 meters minus 0.1 meters. So that's a change of 100 volts in negative 0.05 meters. So that's an electric field of 2,000 volts per meter pointing away from the charge. So that's how we can use finite differences here to estimate the slope of this potential function, which is the electric field. We forgot a minus sign here. The electric field is negative of that derivative, which is why this should come out positive, meaning it points away from the charge. We can also just get a quick visual representation, just like on a contour map. The closer together the contours are, the stronger the electric field is in that location. It's also important to note that if you have these equipotential lines, the electric field will be everywhere perpendicular to those equipotential lines. So this is more useful when we have more complicated shapes, but the equipotential lines allow you to sketch electric field vectors by just making sure that they cross perpendicularly through all of the equipotentials. This tool of potential surfaces is even more useful when we have slightly more complicated distributions of charges. For example, here we're modeling a system in which we have a positive charge located at 1, 0, a negative charge located at 1, 0, and a positive charge located at -1, 0. You can see that the electric field here is going to be the strongest where this surface is the steepest, which is of course a line between the two charges. And in our two-dimensional contour plot, we can see the equipotentials that model this same function here. The electric field vectors are going to be, like we said, everywhere perpendicular to these lines as they cross them. So electric field vectors are going to look like this, leaving the positive charge and landing on the negative charge. I'm not very good at drawing perpendicular to those curves, but we're going to have this kind of shape for a dipole field.